Yes, please.
Please.
Yeah, we can see.
Okay. Please, what's the class size so that we know
Yes.
the number so far, whether we can start or wait a little? Have we formed at least half of the class to start? Or we have not even gotten to half? We are 38 now. Course rep, can we start? Or we have to wait a little for the others?
Doc, it's time.
Okay,
so
we can wait. We can wait for them.
Doc, it's time we can start so that because we have other schedules also after that.
Okay. And then we have
And
recorded.
they have already been confirmed. So,
Okay.
thank you.
I'll record it so that after the class you can have it too, and the slides as well.
Thank you.
Recording in progress.
Good afternoon. You are welcome to FASC 702, Advanced Quantitative Research Methods. We have divided into 4 sessions or 4 lectures who will be taking us through this course. And I will be taking you in sampling distributions, hypothesis testing, and categorical data analysis. Please, if you have a question, you can type it. Because of the noise, I've tried to mute all of us so that we can all benefit from it. If you have a question, kindly raise up your hand or type it at the chat column so that I can pick it from here and address it. Thank you all. So my lecture will be divided into 2, 1 and 2, section 1 and 2. The first one will look at sampling distributions and hypothesis testing. And the second part will look at categorical data analysis, which is very important to us, especially to us who are in the humanities and stuff, and environmental and agricultural sector too as well. So today, we'll look at these 2, sampling distributions and hypothesis testing. I'm Dr. Gabriel Kallah Dagadu from Department of Statistics and Actuarial Science. My office is on the ground floor of the department 008, and this is my email address below on the screen there. Will be accessed on this course, but it will be a continual assessment. So at the end of the 2 sessions, I'll give you a homework or take-home assignment to work on it and submit it maybe in 2 weeks' time or 3 weeks' time. So after the class, we will decide the time range for the submission of the assignment at the second lecture. So I'll begin with sample size determination. Before we can able to do our sampling distribution, we should be able to be abreast with the methods of sampling. So if I don't know how to sample my data, how will I then be able to determine the distribution of our sample? So look at the different types of sampling, both the parametric or random sampling and that random sampling or probability sampling, the non-probability sampling. So under this probability sampling, which is the standard one for statistics or in performing more robust analysis, We have simple random sampling, we have stratified random sampling, we have systematic sampling, we have cluster sampling, and we have multi-stage sampling. So we take them one after the other, then proceed from there. The first one is the most commonest type of sampling, which is the simple random sample. Normally, people call it SRM, SRS. Here, each element or each member of the population that I want to sample has equal chance of being selected because each element is equally likely. So has the same probability of being selected. So we take them, we select the samples that we are needed randomly. So we don't look at people's faces before selecting a sample, or we don't look at the item particularly, but we select our sample based by chance. Normally, it's very difficult to get to your sampling frame. So practically, it's a very difficult process because it's very difficult to select from a population where the sampling frame is not available. For instance, if you want to sample students, which you don't have the sample frame may be the total number of populations or total element of the population, and you number them so that you randomly choose those numbers, then you go to those people and interview them. When you do that, you have performed well. You have a sample frame which you are sampling from. But if you go to the field and just randomly choose observations, you don't have the sample frame, but you only will randomly select the people or interview the people. Though you are performing sampling, simple random sampling, but it has some more its weaknesses. So practically, it's very difficult to develop a sample frame before performing that experiment. But if the sample frame is available, it will become very easy in sampling using the simple random sampling. So in the simple random sampling, you go to the field with your sample frame, then you randomly select your individuals that the number that you want to select from the population, and that becomes your random sample, your simple random sample. In the second case, we have a stratified random sampling. For the stratified, what is done now, you divide the population into groups known as strata. So each one is a stratum, then and the total stratum that you have become your strata. So how do we divide the population or group them into groups? We look for a particular variable of interest that we want to measure from the population. That's why we are sampling. Then we use that variable to have a characteristic with those who are very close, those who have the same similarities, and those who don't have. Then based on that, we perform a simple random sample from each of the stratum. An example is we want to find the average income for a particular company. Let's say University of Ghana employees. We want to find the average income. In that sense, realize that there are some employees or there are some staff who earns below maybe 1,000. There are some who earn maybe 1,000 to 2,000. There are some who earn maybe 3,000 above, and there are some who also earn 5,000 above, and there are some who also earn 10,000 and beyond. So if you go to such a population and you just a minute, please. Thank you. I'm sorry. Okay, if you have such a population, it's very good to classify or to group all those who are earning 1,000 Ghana cedis, below 1,000 Ghana cedis, and group those who are between maybe 1,000 and 3,000, also another group. And also group maybe those who are between 3,000 and 5,000 or 8,000, and those who are maybe 10,000 and beyond. When you do that, then you realize that those in that group have similar endings. Those below 1,000 they are almost all the employees under that category has approximately the same kind of income. and those who are in the middle range, and those who are above the middle range you also have. So in that case, when you are selecting your observations, your estimate you get will not give you just one representation of the higher earners or the lower earners or the middle income earners. It will give you a fair representation of the entire population, so that you may have those who are earning higher, those who are in the middle class, and those who are below the lower class. In that case, when you perform such sampling, we refer to it as a stratified random sampling. And it also has its advantages and disadvantages. So when you do that, you also need a sampling frame too as well in that category. The third one is the systematic sampling. For the systematic sampling too as well, you need your sample frame or your sampling frame, where the individuals in the population will be given a number or a code numbered from 1 to the total, the N, the big N, which is the last person in the population or the last individual in that population. So now what you do is that you take, maybe you want to take the fifth, you want to interview the fifth person in a sequence. So when you start with the fifth person, you go ahead and interview every fifth person from that population. You continue that process until you obtain your required or your desired sample size. And that is what we call a systematic sampling or systematic random sampling. So in that case, if I take the second person, then after maybe 10 observe, after every 10 observation, I take the second person in that sequence, and that will give me this, or that as a rule. So we call the K for case after a random start. So if I start from the fifth person, so every fifth after that person, I count 1 to 3 up to 5. The fifth person I pick again. Then I start again 1, 2, 3 up to the fifth person I pick again. Then continue in that process. So I start with the first. Now, if I'm taking the fifth person, the first member in the this I will not interview him. I go the second, I will not. The third, I will not. The fourth, I will not. The fifth, that's the person I interview. After interviewing that fifth person, I start again 1, 2, 3. The fifth person, I do that. So you continue in that process until your required sample size is achieved. The fourth case is the cluster sampling. Here, our population assumed that to have each group of the population is assumed to have the same characteristics. They have all characteristics. So each group has all characteristics as other groups. So in this case, they have a difference, a little difference between the cluster sampling and that of the stratified random sampling. In terms of the stratified random sampling, we say that each group has similar characteristics, or we call homogeneous. They look alike. But in terms of, and between two stratum or two strata, they have heterogeneous characteristics, meaning the characteristics are different. But when we come to flanking, I'm coming. Let me finish with this so that I address your question. When we come to cluster sampling, here we assume that each group of the population has different characteristics, and have the same characteristics as also the second group or the third group or the fourth group. So when we take a good example is that when you want to sample from a particular community like Muslims, when you go to one Zongo community like Nima, you find all characteristics of Muslim there. When you go to Mamobi, you also find all the characteristics of Muslim there. When you go to Medina too, you find all the characteristics of Zongo youth or Zongo people, Muslims over there. In that case, since the characteristics of Muslim in Medina Zongo, in that of Nima or that of Mamobi are the same, we refer them as clusters. So we perform, after identifying that, we choose the clusters that we want. Maybe it is 2 or 3, then perform our simple random sampling in those groups. And that is referred to as cluster sampling. But in the case of stratified random sampling, within the group or within the stratum, they have homogeneous characteristics. But between two groups, two structure we have for heterogeneous, the characteristics are different. Okay, so Franklin is asking that, please, how different is systematic sampling different from a simple random sampling? In which situation will you be preferred over the other? The simple random sampling is just choosing the individuals in the population at random. There is no order of choosing them. You are just choosing them at random without knowing the actual characteristics of that particular person. But in terms of the systematic sampling, you have a sampling frame, which is just like numbering students from for the whole class, 1 to, or maybe if there are 100 students, 1 to 100. Then you decided to select every fifth person. So if I start, I count 1, 2, 3 up to 5. I pick the fifth person. Then I continue. I start counting a 1, 2, 3, 4, 5. Then I pick the fifth person. That is what we refer as systematic. So you have an order that you pick a fifth, every fifth person. But the random stamp, the first person to start, that one you can choose any particular number. It can be 1, it can be 3, or it can be 8, or any number at all, depending upon the sample, the population size, and the number of observations that I want to select from that population. Please, the one who raised up his hand, can he type his question, please? Emmanuel, Tei, haphazard selection. Well, simple random sampling means that you are just choosing or selecting the individuals at random. That's why I said earlier that you need a sampling frame. And we have something that we call random generation number, random generator, or random numbers. So if you have your sampling in frame, you have your random number generator. Then based on what the numbers that you select from a random number, then you go to your population and go and select that number from the sample frame. So that is how theoretically simple random sampling is done. But practically what is being done is what, Emmanuel, that's what we are calling haphazard selection. Because you don't have the sample frame and just go to the field and just choose, select, interview your people at random. In that case, you don't have the sampling frame and you have not been able to randomly generate the individuals to select from or to interview. So you just go and choose it anyhow. And that is what we refer by as haphazard selection. But it is not a known one. It is a practical or a simple way of doing simple random sampling without having a sampling frame. Okay, Francis, please, the sampling interval chosen by convenience or by scientific calculation. For the sampling interval, for the systematic sampling, it's just choosing at random. It's not by any scientific means. Depending, the only way of choosing it sometimes is to consider your population size. Are you okay? Then you look at the number of observations that you want to pick from that population. And the good thing is that the population is that you arrange in order of a characteristics of the variable you want to pick. So if it is in ascending order, then you arrange the individual in ascending order. Then look at if I have to get maybe if I divide the total population by the sample size I require, will give me 10. So you may decide to choose maybe the 10th person or the 8th person or the 9th person, so that at the end of the day you're able to get your required sample. If you don't get the required sample, then you can start all over again like a circle until you get to your required sample from the population. So when you are using the systematic sampling, it's important to have an idea the total population and the required sample size that you need. That will give you the idea of the particular cave observation to select. I hope your questions are being addressed. Can we proceed? Okay. Then the fifth one, the fifth probability sampling is what we refer to as a multi-stage sampling. In this case, we divide a large population into stages to make the sampling process more practical. So it's a combination of stratified sampling or cluster sampling and simple random sampling. It's usually what is used. So here you have a larger population and you want to sample from that. Maybe due to resources and what time and time of impossible, you divide the population into groups, either into clusters or into stratified what into stratas. Then what you do next is that since you cannot be able to cover the entire what groups, you randomly choose or you randomly select two or the number of groups from that. Then you now go into that or those group and do a random sample again from that. So you may have what a bigger population. Then you divide that bigger population into maybe, let's take Ghana for instance, we divide it into regions. So this is my one sampling unit, this another, this another, this another. So we have a primary sampling unit and you have a secondary sampling unit in terms of multi-stage sampling. So first divide the entire population, for instance, Ghana into regions, and we want to find out maybe the average age or yes, the average age of peer students from primary schools from class 1 to class 6. So in this case, we first divide, we cannot be able to randomly select the entire individual from those 16 regions. So we divide our country into 16 regions. Then since each region has the same characteristics of student in that, we randomly select maybe 2 regions. And from those 2 regions that we select becomes our primary sampling unit. So we select those 2 regions, then we go into those 2 regions and do a sampling, a random sampling of the primary school students from those primary school students from those 2 regions. And that becomes a multi-stage sampling. So first you randomly select your groups, either 1 or 2 or 3. Then from there, you go into the group again and do a random sample. So in this multi-stage sampling, we don't select all observations. We don't select all the first or primary units. We first randomly select some, maybe 2 out of maybe 5 or 1 out of 3, and go into that selected unit to do our secondary sampling from there. In such a process, it referred to as a multi-stage sampling. And I think that can also maybe be done in the field of agric, where we are interested in determining the land which is very good for cultivating a particular crop. So what we can do, we have a very large piece of land which has different characteristics. So we can divide that large piece of land into smaller plots. Then from there, we randomly select maybe 2 or 3 plots where we generate our sample units from those plots. So in that case, we have performed what we refer to as multi-stage sampling. So you divide a piece of land into a plot, then you randomly select some of the plot. Then from the plot that you have randomly generated, then you now go into those plots and do a simple random sampling by selecting the soil sample from those plot and use it for your analysis. So that is about the methods for probability sampling. So we'll look at the second one, the second aspect, which is non-probability sampling. So in terms of non-probability sampling, we have the quota sampling, the snowball sampling. We also have a convenience sampling and judgmental or purposive sampling. So we'll take a look at the one after the other. The quota sampling, as we have here, is a non-random sampling technique in which participants are choosing on the basis of predetermined characteristics so that the total sample will have the same distribution of characteristics as the wider population. Refer to, we are saying that for multi-stage sampling, what is done is that you first have to divide your population into groups. The groups can be clustered or it can be stratified, stratified. Then after you have divided them into groups, then mostly is divided into as clusters. Then we randomly select maybe 1 or 2 or 3 out of maybe the total number of groups that you have. Then the selected unit, that becomes your primary unit. Then you now go into those primary units that you have selected and now do either stratified sampling or simple random sampling or systematic sampling. So based on what the characteristics that you want to measure, you can perform either simple random sampling for the secondary unit or to select a secondary unit or systematic sampling or stratified random sampling. Okay. So quota sampling is a non-random sampling or non-probability sampling or technique in which participants are choosing on the basis of predetermined characteristics so that the total sample will have the same distribution of characteristics as the wider population. So the researcher has already determined his or has a predetermined characteristic that he wants to sample. So he will look for those characters in those elements or embeds that he will select so that the small sample that he may took or the sample may have the same characteristics or same behavior or distribution as that of the population. So he first has to find out, investigate, and know that the elements which has the general characteristics of that population. So those are the ones you do, and that is referred to as quota sampling, which is a non-probability sampling. Then the second one is the snowball sampling. Mostly is used in medical field where members or elements are not willing to participate in interviews or experiment. So a non-random sampling method that uses a few cases to help encourage other cases to take part in the study, thereby increasing the sample size. So for instance, a good example is the case of want to investigate about maybe AIDS patients and stuff. In the first, we realized that it was very difficult for people to go for tests and for us to know that this particular person is HIV positive or not. So they tend to use a few people, those who have availed themselves, to be able to use it to be advert and start. So based on that, you're able to enumerate, motivate, to encourage those who are not willing to come on board to come so that we can get a larger sample size. So also other cases are situations where your elements are very real, cases where you find it very difficult even to identify those who are in that category. We can also use that method to encourage those who found themselves but are unable to own up to avail themselves for sampling so that we can get the required sample size that we need. So the third one is a convenient sampling. Also, in this case, researchers select participants because they are often readily and easily available. So there are some research that are being done. Maybe you want to find out how the cardiorespiratory system of these patients work. You can only go to the hospital and or interview or take raw sample of people who are available, who are already into that situation. That is when in that case you are looking at only convenience, those who are available, those who voluntarily own up. But if the person doesn't, you cannot force the person. So in this case, you work with the sample or the individual, the participant which is available to you to be able to generate your sample or your data. The last one is purposive or judgmental sampling. In this case, a particular persons or events are selected deliberately in order to provide important information that cannot be obtained from other choices based on the researcher's knowledge. So the researcher has a knowledge of what you want to achieve. So he'll go there and select elements or members or in particular items or individuals that can give him or her the result that he desired. So in that case, it's judgmental sampling or purposive sampling. So he only look for his wins. In some cases, most politicians do that. They go to their stronghold and interview their people to make sure that they will say yes, yes to their party. In that case, they will come and say that they are winning with this percentage. No, they just went to where they know very well that the people are for them. So such sampling method or technique is referred to as judgmental sampling or purposive sampling. This is the strength and weaknesses of some of these sampling techniques that we have discussed. The first one is the convenient sampling. That's the least expensive, least time consuming, and most convenient. Meaning it's most popular in our sampling work. And it's not expensive, it doesn't use much time, and it's most popular. So that's the strength of it. And the weaknesses is that selection bias is very common, it's very high. The sample not representative of the population and not recommended for descriptive or causal research. So if you use this, we cannot use it for descriptive or causal research because it's full of bias, it has high bias rate. Then the sample will not be a fair representative of the population. The second one is judgment or purposive sampling. Also, its strength has a low cost, and it's also less expensive, convenient, not time consuming, ideal for exploratory research design. For exploratory data or research design is also very good for that. But its weakness does not allow generalization or subjective. You cannot generalize your result based on that because you select the data that or the people that you want. So you cannot be a generalizer for the entire population, or you cannot do a subjective to you can't do subjective to that result or to your findings. The third one is the quota sampling, where the sample can be controlled for certain characteristics. The strength is that the sample can be controlled for certain characteristics. Selection bias is very high and there's no assurance. Snowball sampling, also the strength is that can estimate real characteristics. when you have situations where characteristics or elements or individuals or participants are very uncommon, they are not common, the snowball is very good in doing that. But its weakness is time consuming. It consumes a lot of time. You spend enough time to be able to attain your result. Simple random sampling, easily understood and result projectable. It is easily understood and what result are very projectable. Difficult to construct sampling frame, expensive, lower precision, and no assurance of representativeness. So its weaknesses that, as I said earlier, it's very difficult to construct a sampling frame, and it's so very expensive and lower precision, and also no assurance or representativeness. You cannot get a high assurance that the data you have selected is a fair representative of the population. So you can have a situation where only one aspect of the world of the population will be represented, while the others will not be represented. And before you can construct your sampling frame, it's very, very expensive and very difficult to do. So that is what its weaknesses. Then it comes to systematic sampling. For this one, can increase the representativeness, easier to implement than simple random sampling, and sampling frame not always necessary. So in this case, you don't always need the sampling frame. Can decrease representativeness, because if you have not arranged your objective of your element or your individual based on the characteristics of measurement in ascending or descending order, then it may also not be a fair representative of the population. Stratify sampling also includes all important subpopulation, and the precision is very high. So it takes care of all the subpopulation, which has a very good representative of the population and has a high precision. Its weaknesses are difficult to list, difficult to select relevant stratification variables, not feasible to stratify on many variables, and very expensive. Maybe you want to measure, you will not collect data for just one particular variable that you want to measure. You may not collect data of students, just you want to know the age, or just you want to know their weight or height. So if you stratify based on age, you will realize that you will not be able to get the correct representative for that of the weight or the height or the income in that order, because you stratify based on the age. So you can only get for one particular variable, but the other variables you will not get a good representative in that aspect as well. Then cluster sampling, easy to implement and cost effective. Easy to implement, cost effective, meaning it's not very costly, and imprecise, difficult to compute and interpret result. It's difficult to compute and interpret result, and if not so precise at that of the stratify random sampling. Ernest, so how does one determine sample framework for data collection? Yes, the sample framework is listing the individuals that you want to select from, the individuals or the elements from the population, and listing them, giving them numbers. Just as we are about to do doing the population housing census, what they did was that they did they list structures. So they go into the community and list all the structures that are available in that community, so that they can be able to go into those structures and interview the people in them. So a way of designing your framework is to list the element, give numbers to all the elements in that population, which is very, very difficult to do. for a very large population or individuals, for instance. But if you are looking at maybe the students of the University of Ghana, already each student has a unique number, which is his ID number. So we have numbers for all of them. So your sample frame becomes the student, which is the ID numbers which you have generated for the student. So if you want to select them now, based on do a simple random sampling, systematic sampling, then you only order your ID numbers in that order, or ascending or descending order. Then you perform more. You select your numbers randomly, your element or your student randomly. So that is how a framework of a sample frame is done. Ernest, is your question answered? Ernest, have I answered your question? Can we proceed? So after we have performed our sampling with all these weaknesses and strengths of the methods of sampling, selecting our samples, there are other things which is very important or key that we should take note of. Realize that almost all the sampling methods that we have listed above, or we have presented or discussed above, has weaknesses and has strengths. So we want to look at some of the weaknesses, what they generate. So what we have is the sampling error. So the sampling error that we'll look at it is defined as the discrepancy between the sample estimate, and the true population parameter. Is what we refer to as the sampling error. So in every sample that we generate, the idea is that it's able to estimate a particular parameter, which is a particular estimate of the population, which is known as the parameter. So the sample estimate or sample statistics will now say, we'll look how close is that statistic or that estimate to that of the population parameter that we don't know and want to estimate. If there's money and time and possible, we will all use the entire population so that whatever we get becomes your parameter that we are known of. But since there is no enough resources, there is no time, and there are some population which is there is no possibility that we can enumerate all the observations, we tend to use sample. So by doing that, we encounter error, which we refer to as the sampling error. So the sampling error is due to sampling variation, because sometimes the sample will not be a fair representative of the population, or there will be some differences between the characteristics or the observations that we took from the sample and that of the population. And if it doesn't give us a fair representative, then we will encounter some error, which we denote as a sampling error. So a statistic, which is an estimate from the sample, Freddy, you are dragging me backwards again. No. That's why I asked if there's any question to proceed. Okay. Please, when you are given the opportunity, let us be fast with our typing of our questions so that I can address them before we proceed. Frederick is asking that why is the cluster sampling technique imprecise and difficult to compute and interpret? Result. What can we do to improve upon it, or which other techniques will be more suitable for handling large populations? The cluster, we said that in clustering sampling, each group is considered to have heterogeneous characteristics, meaning in that group we have different characteristics of interest. So if we are looking at ages, for instance, we can have those who are maybe 1 year old, those who are 10 years old, those who are 20 years old, those who are 50 years old, in that order. So in that precise, there are other also groups which are having the same characteristics. So when you have those groups, you go into that particular subgroup, then you do your what? Simple random sampling. So in this case, you go to a particular cluster, then randomly select your observation. And when you randomly select your observation, it can be that you are only selecting one particular characteristic. That's why I say it is not precise. Or you may have a situation where you may have all the characteristics being involved in the sample. Or you may have only one particular characteristic being selected from that sample, because they are having different variety of characteristics in that particular cluster, as also in the same also in the other cluster. So because they are having a different or high variety of characteristics or individuals in that population or in that cluster, it is possible that we may not have a fair representative of the population of that cluster. That is why it is referred to as imprecise and also difficult to compute and interpret the result. Interpret results that, since you are dealing with clusters, it's very difficult to do a generalization of your result, because maybe some of the characteristics will not be present in at other clusters. Then, unlike the stratified random sampling, is one of the high precise technique of sampling, but the difficulty is that it's very, very expensive to construct and difficult to construct. If you have a sampling frame and you are also able to stratify your population into smaller groups, which are within the groups are homogeneous, and between the stratas our groups are heterogeneous, they have different. In that case, we will have a very good representation of the whole population, which can give us a very precise or very close value to the population parameter. So the cluster sampling will be also the same, or this is just like a simple random sampling in terms of precision. But the only thing is that, since in terms of cluster, you may not have because since you realize that some of the classes have the same, or they all have the same character, you tend to also select only from one cluster and leave the rest. That is a situation where you cannot do a generalization, and it's very difficult to interpret your result. Okay, so I think we can proceed with a sample statistic used to estimate an unknown population. It's not an estimate. Parameter is not an estimate. So potential for extreme sampling error is greater when sampler size of sample as used. So when we use a smaller sample size, we tend to have a very large or extreme sampling error. And there are cases when larger samples are no guarantee of a smaller error too as well. So if you can use a smaller size, and we have an extreme sampling error. And it also doesn't mean that if you have a very large sample sizes, we may have a smaller sampler error or a smaller sample error. So what we do that is why the techniques of sampling were able to help us to be able to arrive at a very small sampling error. So the idea of having different sampling technique is just to reduce the error and also to minimize our cost effective. So sampling error can include both systematic sampling error and random sampling error. So sometimes we can perform simple random sampling and have a very large population, but that will not guarantee that we will not have an extreme or a large error, or that will not give a guarantee that we have a small error. It may happen that it will even give us a larger error, but we can have a small sample and that will even give us a smaller error, sampling error as compared to a large one. So one of the best technique is the stratified random sampling, which able to stratify, but its difficulty is for us not to be able to stratify the variable based on many variables or characteristics of interest. So the two sampling errors that we can have is the systematic sampling error and the random sampling error. So we look at them. One we have control over and the other we don't. Let's see how we can eliminate the sampling. That we have two sampling error. We have the systematic sampling error and we have the random sampling error. So with this, we're able to determine where to get our sample error from. We can eliminate our sampling error, but not all. One we can control, that's increasing the sample size to be able to reduce the what? We cannot totally eliminate, we cannot totally eliminate our sampling error, but we can reduce it. We have control over one of the errors. There are two. We have the systematic error and we have the sampling error. A systematic error can be what? Reduced, but the random error cannot be what? Eliminated. These are due to what? Your your method or your technique of sampling. So there are some techniques that were some of the things that we have in the field when we are collecting the data that may be due to the negligence of the researcher or the one who sampled the data or the enumerator. Some of these can be reduced to have a very small error, but there are some as a result of the population and sample size. We cannot eliminate all. So the random one cannot be eliminated, but the systematic one can be reduced or eliminated. So another challenge that we may encounter in choosing our sample size is the sample size determination. We are always confronted with the question of how large a sample should be drawn. The size of the sample depends on various considerations, including population variability, statistical issues, economic factors, that's money, availability of participants, and the importance of the problem that I want to solve. And there's some instance like dealing with human life and stuff. There is a 1% or 0.01% of population can mean a lot, while in other populations, even at 1% may be considered something which can be allowed. So depending upon the availability of participants, the importance of the problem, the economic factors, the statistical issues and the variability of the population will tell us how large our sample should be so that we can have a more accurate or precise or estimates to that of the population parameters. So in inferential statistics, the sample size required depends on how big a difference between two groups you want to be able to detect. With large sample sizes, small or the difference between your parameter or that's the variability in that population, the variance, or the sample mean of a randomly generated sample from that and that of the population mean. So if you are looking at two different groups, then we are talking about two different groups of population. Then that's one, we can look how variable they are in that particular population. Or we can also find out the variability in the observations in that particular population, where we can measure the sample size. We can look at the variance or the standard deviation of that of the population. Samuel Akwesi Adakwa. We'll come to that, please. Effect size and sample size. So I'm coming one after the other. We have just talked about sample size, which how to determine it. Right? So in the sample size, if the sample size is sufficiently large, virtually any population difference will result in statistical insignificance. Statistical significance. Meaning that if you have a very large population and the sample size is also sufficiently large, then the difference between the estimate and that of the population parameter may be as a result of a statistical significance that we need to contest. We need to contest or do a hypothesis test to determine how significant is our what, or how variable is our estimate from that of the population parameter. On the other hand, the smaller the sample size, the larger must be the population differences to achieve statistical significance. And if the sample size is small, then the population differences between the two populations that I want to measure or want to sample from, their variability within them must also be very large so that we can be able to achieve a statistical difference between the parameter or the estimate that I want to compare with that of the parameter that I want to estimate. The statistical difference significance is by performing the hypothesis testing. So, Samuel, Adakwa, the sample size, the difference between the effect size, you are trying to measure the variability between your observed what? That's your population parameter that I want to try to estimate by the sample. So we look at how big or what is the variability between that. So we're also able to determine the sample size. So depending upon how large the variability is, it also tells you the sample size to be able to how large the sample size will also be for us to be able to estimate more accurate results for our population parameter. So if your effect size, that the variability is very small, then your sample size can also, you don't need a very large sample size to be able to measure or estimate a population parameter. So based on the variability in the population of the characteristics of interest, to determine how large your sample size should be to estimate more accurate result. But the underlying fact is that we want to estimate the population parameter, if it is the mean or if it is the proportion or the variance. We should be able to see what should be our sample representative. We can be able to measure that particular unknown parameter that will be more accurate or almost the same as that unknown one. So we use a sample to do that. So the effect size is the variability, and the sample size is how large the sample we should choose. So several statistical formulas are available for determining sample size. We have the one where the Cochrane has one which talks about the proportion of two groups We can also have ones which we can use the variability between the population mean and the sample mean, or another one which we can also use the coefficient of variation as what? The variability between the estimate and that of the parameter. So several statistical formulas are available for determining sample size. The Cochrane formula allows you to calculate an ideal sample size given a desired level of precision, desired confidence level, and the estimated proportion of the attribute present in the population. So if you look at the attribute present in the population, then we can use the proportion. Okay, so I'm saying that if we look at the attribute present in the population, and we are looking at the proportion, which we estimate as a P. So we look at the population proportion P and use that. So the population proportion is known, where Z is the corresponding confidence level required or Z value, and your E is allowable margin of error or desired margin of error that you want to allow for your estimate between that and that of the parameter. Notwithstanding, if we are not talking about the attribute of the particular population of groups, we can also define our N, our sample size, to be equals to either Z alpha on 2 squared. Then we have sigma squared, that's the variance, divided by what? The allowable D or E squared. There's the margin of error. So either D or E, any one of them, the margin of error. Or some may also use this, some may also use your T. Maybe they have estimated what? A sample size. They have estimated your sample statistics, like the mean over 2 times the coefficient of variation, which is defined as the sample variance, sample standard deviation over the mean, and all divided by what? Error, the margin of error. And this one is also squared. So if we are not talking about two population or attributes in the population where we require to estimate our proportion or proportion given, we can also use any of this thing. And depending upon the area of study or your attribute of interest, that tells you the kind of formula to use to estimate your population size. Frederick's question is, what are your views on using sample size calculators which seem simpler instead of the complex mathematical formulas? In fact, in performing a research as a PhD student, your supervisor or your examiner who examine you want to see how you arrived at your sample size. What are the things you consider? So it's very important to what? The calculator method that will help you to do that, but it's very important to state or to derive your sample size by using acceptable and scientific method. Don't forget your sample size calculators also are built based on what? This information. So that's only give you that's your implementation stage or calculation stage. But behind what you see, they have developed these methods which will help you to do. So you have to supply this information for you to be able to come out with your required sample size. So maybe you are in hurry, that's what you can do for academic work. You need to, that's a scientific work, you need to show or explain how you attain your sample size, what level of significance you choose, what desired level of precision or margin of error you assume, what was your variability, or what was the proportion of attributes, or what was the coefficient of variation. Freddy, is that okay? Some may ask in the field of, or maybe you want to estimate the density of a soil for a particular crop or for a particular land. In this case, you don't know even the attribute. So what you can do is that you can randomly or collect some of the soil content and measure, select at least some of them and measure the quantity of the soil. Maybe if you are looking at the content of density, content of moisture in that soil or that particular attribute that you want to measure, then you use that to calculate your mean and that of your standard deviation. Then from there, based on the sample you generated, you calculated, it will help you to use this formula to estimate the required sample size that you will need for you to be able to get a very precise accurate result or estimate for your population parameter that you are looking for. So, for example, suppose we are doing a study on the inhabitants of a large town and want to find out how many households serve breakfast in the mornings. We do not have much information on the subject to begin with. So we are going to assume that half of the females, the families serve breakfast and half do not serve breakfast. So this gives us a maximum variability of maximum variability. So half serve breakfast, half doesn't serve. So we have P, the proportion of those who serve breakfast is 0.5. If you also know that in that particular population, maybe only 20% of the people who serve breakfast, then in that case, then your proportion will be 0.52. But if it is unknown, since we don't know, we can assume, because to be able to achieve a maximum population sample size, we assume that your proportion should be equal to 0.5. So now since we don't have a knowledge. So, and there's another thing that we should know is that when we have a larger sample size, we tend to have more accurate result than a small sample size. But that doesn't give us a guarantee. So if we have the maximum sample size that we need for the study, it is better than we go and get a minimum or an unacceptable sample size, which will give us inaccurate estimates. So we always, if we don't have idea about the characteristics, then we choose our proportion to be 0.5. When we are looking at the proportion. Now let's say we want a 95% confidence on our unknown parameter. Then then at least 5% plus or minus precision. Then if that, a 95% confidence level give us a Z values of 1.96 per the normal tables. When we calculate that from the normal table, we have 1.96. Then, and we are given a 5% allowable precision on our estimate. That's the margin of error. So we are going to have our sample size to be given as Z squared times the P into 1 minus P over the margin of error. So that will be 1.96 squared, 0.5 times 0.5 over 0.05 squared. And that will be approximately 385 what, as the sample size. So this sample of 385 households in our target population should be enough to give us the confidence levels we need. That's the 95% confidence level that we need. Maybe if we know the attribute, we may have a lesser sample size that will estimate our desirable level of what? Precision that we want. But since we don't have an idea, we choose the maximum, that's 0.5, to be able to arrive at this 385 as our sample size. If the population we are studying is small, we can modify the sample size by we calculated in above formula by using this equation. For instance, if the sample size, the population is large, is small, and the sample size is so big, they realize that the ratio of the sample size of the population is greater than 0. Is greater than 0, is greater than 5, that's 0.05, or some to 0.1, that's a 10%. Then we cannot adjust it and take a smaller sample size because we don't have enough money to take larger sample size. So don't forget, we choose the maximum. So if the sample population is not too large, then we can adjust it to get a minimum population, a sample size that can be used for our study. So in our example, we had 385, but if the population is just 1,000 houses in that community, so you realize that getting 385 sample observation household will be too large. Maybe you don't have enough resources. So we can find the what sampling fraction, which is what the sample size over the population what size. Then use that to correct, and that is done by using this formula. So your required sample size that will give you the good estimate will be the initial sample size we estimate, which is 385 divided by 1 plus n naught minus 1 over n. And this will give us, one from this example, will give us 278 observation. So realize that when you divide 385 by 1,000, we are getting 0.385, which is greater than or even 10%. So we need to correct that to get what? It's too large. So we need to get a more smaller sample size that will be good, that we can reduce our cost. So in this case, our households will now we need 278 households in our sample to be able to generate a result that will give us an allowable 5% margin of error. So if that is okay, if you don't have any question on sample size, then we can go ahead to look at what the sampling distribution of some of the estimates or the statistics or the parameters. Okay. We use Francis. We said that what for us to be able to correct with this formula, your population size should be small, and the ratio, which we call the sampling frame fraction, your n naught divided by big N, if it is greater than what? Some use 0.05. If it's greater than 0.0, that's 5%, then we should correct it using this formula. If it is less than 0.05, then the population size is large enough to maintain your sample, the initial sample size. But if it is greater than 0.05, then we need to correct. I mean, the sample size is the population size is too small for the sample size that we have calculated. Or some also use 10%, that's 0.1. So depending upon what you are estimating, the variability in the population, and also the economic implications, or how large the sample size should be, you are able to determine the population as either 10%, the sampling fraction should be greater than 10% or 5%. For comfort, for the maximum allowable margin of error, mostly is based on the case or the situation at hand, or what you want to estimate. But so I think that the best way to be able to determine your maximum margin of allowable margin of error for a particular case, it may vary from one department to another, or one or case to another, or one research to another. I think literature should be able to guide us to be able to actually in that particular field, what is the maximum allowable margin of error for an estimate. In a clinical trial where lives of human beings are involved, if you give 0.5%, it is too big. They can even say 1% is even too big for a maximum allowable margin of error. But when we are dealing with individuals of responses or other things, which doesn't involve the character, doesn't involve life of the human being, then in that case, even 5% can be considered as okay, as maximum allowable margin of error. So based on the issue at hand and what the variable of interest or characteristic of interest I want to measure, I think literature should be able to help us and guide us with the maximum allowable margin of error to use, so that we'll have very accurate and excellent results. Comfort, have I answered your question? Are we okay? Can we proceed, class? Yes, I know you people are me, so I wanted you to use the chat column so I see all the messages and react to that. Thank you. So our next thing that I'll look at is the sampling distribution of the mean. So we want to look at the sampling distribution of our statistics. That's the mean, the proportion, and also the standard deviation or the variance. We know that mean is a random variable. The sample mean is a random variable. Proportion to the sample proportion is also a random variable. And the sample variance is also a random variable. So they also have a distribution that or the way they behave, we call it distribution or law. So if you can plot it and also see how it behaves like normal random variables that we took, or observation that we took from our population. So, and that brings us to the first one, the sampling distribution of the mean. A sampling distribution is the distribution of a statistic under repeated sampling. So repeated sampling underlined. How do we refer, what is what we refer repeated sampling? For instance, I have a population of 100. Then, due to economic constraint or difficulty, I cannot enumerate all the 100 elements or observations. So I have to maybe pick only 10. So select only 10 out of the 100. So if I randomly generate 10 items of these observations, of this 100 population, I'll be able to measure my observation, my population parameter based on the sample, using the sample statistic. So if it is the mean, then I'm able to estimate the mean. But you know very well that the sample mean that I estimate will not be exactly the same as the population mean or the population parameter. If I were to estimate the entire 100 or enumerate the entire 100 participants or individuals in the population, the value of the sample, the mean of the 10 people will not be exactly the same as the mean of the 100 people. It can also mean that it is the same. It can also mean that it will even be less than the mean or even be greater than the population mean. So if I am able to do that sampling, I did it and I put that observation down, the mean down. Then another person also sample from the same population, where the sample is also different from my first sample. But it can also mean that if I say different, means that I don't take the exact number of observations that the person also took. If my 10 observations, and then the second person also took 10 observations from there, but maybe the difference may be there's one individual in mine which is not in his, then what? And there's one individual in his which is not in mine. Then we also have two different samples. So when you also did this and calculate his mean, you realize that he also have a different mean, sample mean as to that of mine. So when we continue in that process and we're able to exhaust the entire possible samples, the type permutations that we can do to get our possible samples from that 100 observations, then we'll have different sample mean. So we'll have if there are 100 possible samples that we can get, then we'll have 100 samples and have 100 sample means. So the plot or the behavior of this 100 sample means that we generated or 100 samples from this 100 sample mean is what we refer to as the sampling distribution of the sample statistic mean. So we have done that. We're able to generate the sampling distribution based on repeated sampling. We sample and sample and sample and sample. Then we come out with a behavior of the sample mean, and that becomes the sampling distribution of that statistic. So in other words, it tells us the values that a statistic takes on and how other it takes them on. We use the sampling distribution of a statistic to assess the sampling error of an estimate. So a random sample is a set of independently identical distributed observations, S1, S2, S3, Xn. Why do we say they are independently identically distributed observations? They are identically distributed because they are coming from the X1, S2, S3, the element of the sample are coming from one particular population, which we assume that each individual behaves as the population. So each characteristic represents that of the population. So that's why they say they are identically distributed. Independently means that we randomly select these individual observations. So selecting the first one is independent of the second one. So we randomly generate this sample from the population. That's why we say they are independent observations. Identically, meaning they are coming from one particular population which has a behavior. So all those variables, all those elements also behave like their mother population. So when sampling from a large population with or without replacement give the same result. We have what we call with replacement and without replacement. When a population is very large, like 1 million, and relative to your sample size, with replacement, you select the first one, you substitute it and pick the second one again. You put it back, you put the third one. That is what with replacement. The result you get at the end of the day from our estimate will be the same as when you substitute. You don't put the element back before you select again. In that case, but if the population size is small, then the results will be different. If we assume that the population has mean mu and variance sigma squared, how does the sample mean S bar, which is defined as the summation of xi from 1 to n over n, vary on repeated random sample of size n? So sample 1 of size n, we finish and put it by resample again. We do that repeatedly. How will this sample mean behave? The behavior of this sample mean is what we are referring to as the sampling distribution of the mean. The central limit theorem states that any distribution, no matter how skewed or strange it is, will produce a normal distribution of the sample means if you take large enough samples from it. We can have what the central limit is trying to tell. This is why most often when we have a very large sample size, we tend to say that our observations or our characteristics that we measured are normally distributed. So that we use the T test and other things or the Z test to be able to perform our analysis. It's because of this law or this theorem, the central limit theorem, that so even though the distribution that we sample from is not normally distributed, it's either positively skewed or negatively skewed or flatty or whatever, or strange it is, each sample mean, when we want to perform the test for the mean, we assume that it is normally distributed because of the central limit theorem. And when we say the sample is large, it means that large enough. Some books say 25 and above, some say 30 and above. Then we consider as large enough. This is of great importance in statistics. It allows us to use the properties of a normal distribution when analyzing data, even when the data we are analyzing is not normally distributed. For this, what the central limit theorem is stating, for any distribution with mean mu and standard deviation sigma, the distribution of sample means converges to a normal distribution with mean mu and standard deviation sigma over the square root of n. The standard deviation, the population standard deviation over the square root of the sample size. And it's stated like this. The sample mean is normally distributed as the population mean mu times and the variance is a sigma squared over n. And sigma squared is the population variance over the sample size. How do we get the population mean? All that we are saying is that when you are able to get all the possible combination of samples from the population, then the means of all these samples When you find the mean of all these mean, and that is what we call the expectation, and to be equals to what? The population mean. In that case, each individual in the population has been taken care of. So in that sense, the mean you have will be equals to what? The population mean. So the mean of the sample, all the samples mean, all the samples mean will be equals to the population mean, and that is called the expectation of the random variable x. Then your variances, the variance of this sample variances will also, the expected value of this sample variance will give us sigma square over n. So the expected value of this sample variance will be equals to sigma square over n. Sigma square is the population variance divided by what? The sample size. So by central limit theorem, for any distribution with mean mu and variance sigma square, the distribution of the sample means converges to a normal distribution with mean mu and standard deviation sigma over n, the square root of n. So with effect, this is what we call the sampling distribution of the mean, is what we call as this. So the sample mean follows a normal distribution. The parameters are mean mu, that's the population mean, and the variance is sigma squared over n. So that this is what we call the sampling distribution of the sample mean. So when you are sleeping, they ask you what the sampling distribution of the sample mean or the statistic, you should be able to state that it follows a normal distribution with mean, that's the mu, the population mean, and the what? The variance is what? The population variance divided by the sample size. With that, I move to the proportion. For let x be the number of successes in a sample and be distributed as a binomial random variable x following binomial with n as the number of observations and p as your success probability. Where n is the sample size and p is the proportion of successes in the population. So if you have we have an attribute, two set, and your successes is one particular, that is your one particular attribute, and the remaining attribute are your failures, then the proportion of what? X, the number of the attribute you are into becomes your proportion, that's P. And the ones which are not of interest, attribute of interest to you, that becomes your failure, that will be 1 minus P, sometimes we know as Q. So our interest is want to estimate that particular proportion in that population. But we cannot do that since we cannot cover the entire population. We use a sample for that. So all that we do is that the sample size, we first estimate the sample proportion. It's a random variable, that's p cap, which is what? Is x, the number of attributes for successes over a total sample size, and that will give you the sample proportion p hat. But your population proportion is given as p, which equals to a total number of observations which have that particular attribute over the total population size. So our interest is to able to estimate this population proportion p, but since we cannot enumerate the entire population, we will use our sample proportion p hat to estimate our population proportion p. So if numerous random samples or repetitions of the sample of the same size n are taken, the distribution of possible values of for p hat, that the sample proportion is approximately normally distributed with mean P, that's the population proportion, and standard deviation, sigma P hat to be equal to the square root of P into bracket 1 minus P over N, and which is also given as SD P hat. So your standard deviation or for the proportion, the sample proportion, is the square root of P into bracket 1 minus P over N, and the variance equals to P into the 1 minus P over N. So for the sampling distribution of the sample proportion follows a normal distribution with mean the population proportion P and your variance, the population proportion P into bracket 1 minus the proportion divided by your sample size. So we have known that the sampling distribution of the sample mean follows a normal distribution. Also, the sampling distribution of the proportion follows a normal distribution. That is why if you want to test for significance for the variability between the population parameter mean and the sample mean, we use the normal distribution or the T distribution. If they depend upon the sample size. If we want also to perform compare the proportion of characterizing the population to that of the sample proportion, we also use the normal distribution to perform to test whether they are the same or different, or significantly different, because of their sampling distribution that they follow. So we'll now look at the sampling distribution of the variance or standard deviation. Suppose that x1, x2, etc. to xn are observation of a random sample of size n from normal distribution, x following a normal distribution with mean mu and sigma and variance sigma squared. The sample mean s bar is defined as this, and the sample variance is also defined as what? The summation xi running from 1 to n. The sample variance we use small s squared. Xi minus the sample mean squared divided by n minus 1. When you have to find the population variance, when you are using the entire population, then we will have a summation of xi minus the population mean squared over the total population size. Then we are saying that the sample mean x bar and the sample variance sigma squared are independent. Since they are independent, even though in computing the sample variance, we use the sample size, the sample mean in it. But this is telling us that they are independent because they have different distribution. The way they behave, the sample mean is different from that of the sample variance. So that's why we say they are independent. So your sample variance follows a chi-square distribution with n minus 1 degree of freedom. N minus 1 is a constant, and population variance is also a constant. So if I divide this by multiply it by x squared, I'm getting a chi-square with n minus 1 degrees of freedom. So in this 2, the only one which is a random variable here is your sample variance. N minus 1 is a constant, and sigma squared is also a constant. So your xi minus s bar squared over sigma squared follows a chi-square with n minus 1 degrees of freedom. So that is the sample variance x squared is distributed as a chi-square with n minus 1 degrees of freedom. So that is why when we are testing for significance of variance, or we are performing one-way analysis of variance, we use the F test. And the F test is a ratio of 2 chi-square distribution. And also, the F test is based on the ratio of 2 variances. 2 variances. So that is why we call it also the chi-square, the ratio of 2 chi-squares. So from here, we have note that the sampling distribution of a mean is follow a normal distribution. The sampling distribution for proportion also follows a normal distribution, while sample distribution of variance follows a chi-square distribution with n minus 1 degrees of freedom. So this is the summary of what we have looked at in the first part of that sampling distribution. Understanding how the sampling distribution is created and used may be the most important factor in learning about statistics. The sampling distribution is the distribution of a sample statistic which is created by repeated sampling from a given population. Second, the estimates, that's the proportion, the mean, and the standard deviation of variance of the sampling distribution are related to parameters of the original population. Third, the connection between the sampling distribution and the original population is at the heart of statistical inference. So that is what you're coming to do at, that's a test of hypothesis. Any question, please? Is there any question, please? If there's any question, just put it here on the chat column that I address it before I move to the next session, the next part, test hypothesis testing. Are we there? Can we proceed? Or we are exhausted? Okay. So now we look at what? Hypothesis testing. After knowing the sampling distribution, collecting our sample, estimating our statistics or our estimates or our statistics, we know how they behave, the distribution of that. But we have been told that there are some errors that we need, or we have systematic error that we can be able to reduce as a result of what? Some of the things that we perform in the field, some of the behavior of the researcher, and there are random errors that one we cannot have, we don't have control over. So because of that, our statistics will not be the same as that of the parameter, that the population or parameter. So we need to perform scientific tests to establish whether there's wide differences between the estimate that we have computed and that of the population parameter based on the behavior of that estimate and that of the population parameter. So that brings us to statistical inference and the hypothesis testing, which is under hypothesis testing. So statistical inference is the art of generalizing from sample data to a larger phenomenon, the population, with calculated degree of certainty. So we are trying to do a generalization of the data that we have collected from the sample to that of the population with a calculated degree of certainty. That is why when you have to perform a hypothesis study, it's going to say 95% or 90% or 99%. That is the degree of certainty that you have tested to be sure that what our result we can generalize and say that maybe 90% of our result is what? Is the same as the population parameter or not. So that's the degree of certainty that we are talking about. So hypothesis test, a test of hypothesis or significance test, is a procedure designed to assess what the evidence provided by the data says about some statement about the population parameter. So we wanted to find out whether the evidence that you have gathered from the data is the same as the population parameter that you are trying to measure or estimate. So steps involved in hypothesis testing that we need to know. If you have these steps, then life will be easy for us when we are asked to perform it or we are doing it at any level. The first step is to determine the appropriate null and alternate hypothesis and set the level of significance, alpha. 2, check assumptions for performing the test. Three, calculate the test statistic and determine the p-value or the critical value. Then 4, evaluate the p-value and report a conclusion in the context of the problem. You have already estimated your value, your sample mean, but I want to generalize it to the entire population, see and find out whether what you have estimated, because the population parameter is unknown. So how sure are you with what degree of certainty that what you have estimated from the population, from the sample, is a true reflection of the population mean or the proportion or the variance or what? So you need to first state or determine your appropriate null and alternate hypothesis. Some call it H0 and HA or H1. Then set the level of significance alpha. The most common ones are 0.01, 0.05, and 0.1. Some even have 0.005, depending upon what the issue we are discussing or issue you are. But the most common ones are 0.0, 0.01, 0.05, and 0.1. Then after that, you check assumption for performing a test, whether the data you have satisfy those assumptions. Then you calculate the test statistic and determine the p-value or the critical region, or the critical value or the region. Then evaluate the p-value and report a conclusion in the context of the problem. Don't just say I reject and that is all. You have to conclude based on the problem at hand or the problem you are solving in that context. So stating the null hypothesis and alternate hypothesis, how it's being done. The null hypothesis, normally denoted as H0, has 3 ways of stating it. State the assumption or numerical to be tested. So it states the assumption or the numerical value to be tested. It begins with the assumption that the null hypothesis is true and always attain the sign, the equality sign. So it states the assumption or the numerical value to be tested, or it also begins with the assumption that the null hypothesis is true, unless proven otherwise. So you have the notion that's what you are testing. You are testing that it is true. You want to find out whether because you have estimated your statistic, which you want to estimate the population parameter. So you are sure that the value you got from your sample is the same as the population. So that's why we are saying that we assume that the null hypothesis is true and it always contains an equality sign. Equality sign means no difference. So some can use there's no difference between the sample estimate and that of the population parameter, meaning you are talking about equality. The alternate, on the other hand, is denoted by either A with subscript H subscript A or H with subscript 1. And it's the opposite of the null hypothesis. It's a complement, also the complement of the null hypothesis as H naught. Challenges the status quo. Tells you that it challenges that the assumption that the null hypothesis is not true. So the alternate is saying that the null hypothesis is not true, while the null is saying that your statement, the assumption is true. Then 3, it never contains the equality sign. So either not equal to, or is greater than, or is less than. Or other ways sentences form is all they are different. The difference between the two groups is generally the hypothesis that is believed to be true by the researcher. So that is what normally the researcher tries to establish that the null hypothesis is false. So I'll settle on the alternate hypothesis. So he first assumed that the null hypothesis is true, but believe that there's a significant difference. Generally, the alternate hypothesis is the true, is supposed to be true, believed to be true. So these are the clues that we need to know when we are setting our null and alternate hypothesis of our problem. So we have two types of hypothesis. We have a one and two-sided test. So hypothesis test can be a one or a two-sided tail test. And we have a one-sided tail or directional test. That's another name of it. One-side tests are directional. So, for instance, when we are testing the mean with the population mean, we are saying that the estimate from the sample is what? Less than or equal to what? The population mean. That's what you are testing to. And this is what? Directional. So the versus, this is the alternate one, which is what? Mean greater than or mean not. This is a one-tail test. And there's an equality, meaning less than or equal to H mu naught. Here is what? Greater than or mu naught. So if I have my number plane, my line, and this is my mu naught. So we are saying that what? One starts from here. That's why I say they are opposite. One is saying from here to, that's what the first one is saying, that is your H naught. And the alternate is saying that what? Is here. From your linear program or your inequality analysis. So if you don't change the remains, that value is not included. So this is for H1 and this is for H naught for the first hypothesis, and we call it directional hypothesis or one tail test. The second one, it can be maybe you are comparing two means. So we are saying that the two population means are what? Greater or equal to 0. Those also are another directional test. And we can say that they are strictly different. The two population means are different, meaning that the difference between them is less than 0, meaning they are different, or greater than 0. In that case, too, we refer to this also directional or one-tail test. But for two-tail test, we say that the mu is not equal to mu naught, meaning there is no difference between the two of them. And here the versus the alternate is saying that there's significant difference between them. They are not equal. So this is for two-tail test, which is not directional, non-directional, or mu1 minus mu2 equal to 0, H naught, versus for H1, which is mu1 minus mu2 is not equal to 0, meaning it has negative or positive. This is also a non-directional test, two-tail test. So basically, these are the two hypothesis types that we have, one tail and two side or tail test. So test statistic and the p-value. After we have stated our test, we have stated our hypothesis, we need to check our assumptions. Then from there, calculate our test statistics and the p-value. Most often, we perform the analysis using the software. We don't do it manually. And the result is given to us. Sometimes we don't even know which one is the p-value, which one is the test statistic, and we mix them all up. Sometimes we compute it manually. Then we determine the critical region. From there, we can able to compare the statistics to the critical and find out whether we have to reject the null hypothesis or we fail to reject the null hypothesis. So to calculate a test statistic in the sample data that is relevant to the hypothesis being tested, and that will be based, or the test statistic will be based on the distribution of the sample statistic that you are testing to that population parameter, you are comparing to the population parameter or the inference that you are doing. Then two, after calculating a test statistic, we convert this value to a p-value by comparing its value to the distribution of the test statistics under the null hypothesis. So the null hypothesis has the distribution of the sample statistics that you were trying to compare with the population parameter. Measure of how likely the test statistic value is under the null hypothesis is that if our p-value is less than or equals to alpha, implies that we reject H naught at the alpha level of significance. But if the p-value is strictly greater than alpha, implies that do not reject H naught at level of alpha, at the significant level of alpha. So if your p-value is smaller than alpha or equals to alpha, that means that we can reject our H naught and say that there is significant difference between our population parameter and our sample estimate. But if our p-value is greater than alpha, it implies that the difference or the variability between the parameter and the estimate is not significant statistically. So we do not reject H naught at that level of significance. So we have what we call rejected region and level of significance. Alpha specified before an experiment to define the rejection region. So it's important that we specify the alpha, the level of significance at the beginning of the experiment, so that we can be able to determine the rejected region or rejection region, so that we don't force to reject when we don't need to reject, or we force to fail to reject whilst we need to reject. So the rejection region, set of all test statistic values for which H naught will be rejected. That's what we refer to the reject. So we can have a one-sided or one-tailed test where this area is referred to as the rejected region. This small area under the curve from the red line to the left is referred to the rejection as alpha equals 0.05. But for a two-sided test, the alpha is equal to 0.05. It means that here in the first case, the area under this curve is your probability, which is given as 0.05, which is the same as alpha. So the area under this curve here is 0.05, which is the level of significance. And from here upwards to infinity is giving us the probability, which is 0.950. And when the statistics fall in this region, then we do not reject H naught. When it comes to a two-sided test or two-tailed test, this at alpha equals 0.05, we split the alpha equals 0.05 into 2, and that will be 0.025 and 0.025. So the area under this curve at this point is 0.025, and also the area under this curve is 0.025. So the value corresponding to the red line here is negative 1.96. And also the value corresponding to the red line and the horizontal line is positive 1.96, where 0 is here. And this is giving us a normal probability curve. a standard normal probability curve where the mean is 0 and the variance is 1. So these are the types of regression regions we have. We have the two-sided or two tails one, and we have a one-tail side. If it can also be, the tail can also be for regression, can also be at the right-hand side, which is here, or left-hand side, as we have here, left or right. That's a two-tail test. Errors in hypothesis testing. Can we complete it? Or we pause here and continue next time because it's now 3 o'clock? Hello, class. Okay. We are left with at least 12 slides to go. 12 or 13 slides to go. About 14 slides to go. So we can continue next week and also look at the other one, which is categorical data analysis. Okay. So as the majorities carry the vote, we'll pause here. If you have questions, let's ask before we continue, not really next week at 1 o'clock, the same time. Okay, thank you all. I've unmuted you. If you have a question, you want to speak to it, you can do that.
Recording stopped.
Good afternoon, Doc.
Good afternoon, Jane.
Please, would you send us a recording?
Yes,
Would you have it?
Yes,
All right.
I'll send it to you.
Okay, thank you.
Welcome. I'll send you the slides too as well.
Okay, doctor.
Okay. Ken, I'll use the practical example with me next week to explain them. Is that okay? I'll do that. So thank you all for coming. I'll send you the video and the slides. Lord willing, we'll continue next week.
Okay, thank you, doctor.
Thank you.
Okay,
too.
Thank you, sir.
Thank you.
Welcome.
Thank you, sir.
Thank you.
Thank you.
Thank you, Doc.
People were sleeping.
Thank you.
Thank you.
How did you know?
All right. Okay. No interesting. Oh, big question. Let's see it. You want to play? Yeah, let's do it. Hey, look at him. Hey, what a big no you. Was it a file?
Bye bye.
Bye, say. Dagadu.